This is James Grass, and this is my Live 5 presentation. Faraday's law relates time-varying magnetic field to a Curly electric field. This field provides an EMF that can drive current, which produces a magnetic field which exerts a force on the source of the external magnetic field. In our case, the source of the field is a falling bar magnet, and the induced current is driven in a tube of aluminum foil. In the lab, I will investigate the interaction between the falling magnet and the tube of aluminum foil. To do this, I will collect data on a magnet falling through a tube of aluminum foil, model said magnet computationally, and compare the two results. This is the data I got from doing the drops of magnet through the tube. Using the video, I found the time of entrance and the time of exit. Took the difference, and that is the time the magnet was in the tube, and that averaged to 1.875 seconds. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. What color corresponds to the clockwise current? Well, the band is red, so it was counterclockwise, and by that logic, blue is clockwise, but the R's band on top and bottom was red, which was a little weird, but that meant that the direction was counterclockwise. If we were to flip the magnet around, it would be blue and the current would switch direction, but the velocity would be the same. The total time in tube would be in the computational system was ridiculously fast compared to what we saw in real world, which was very weird. 0.241 seconds in the simulation and 1.875 in the real world. The shape of my plot tells me that the forces of both gravity and magnets are acting on each other. It was pretty close to linear, but that should still be showing both effects. If the resistivity of the conductor was close to zero, the magnet would fall slower because the current would be stronger, so the magnetic force would be stronger. And by the same logic, if there were holes in the tube, it would fall faster because there would be more resistivity in the tube. Now I'm going to walk you through my coding. There's the physical constants, then the graph initialization, which are all given. Then I had to create our geometry of my tube and foil. So this is the length, width, and a radius, and the radius calculation. Then there's the more numbers that I wasn't supposed to edit. And then I created my bar magnet. So I put in the mass, and then lines 73 through 78 are just the computation from line 3 to give me my magnetic dipole moment of the same magnet. Then I had to visualize the bar magnet. Then I have my definition of dipole calculations function, which I created in line 3, and then I created my flux, my delta flux over delta T calculation, which was very complicated, but I basically just used the formula from the video 43, and this is just the code that represents that same formula. Then it's a lot of given stuff to generate the bars and the rings and the calculations for the graph, but I calculate my ring current, as you can see, with the delta flux over the ring radius, and then down towards the bottom, the calculations for the B at the ring, B hat, sine theta, and all of that to compute the typical B field at each ring. And then at the very end, we've got the bar velocity and bar position calculations that rely heavily on previous segments, and then the print lines. And then over to the right, you can see my magnet falling through my tube with all red and my velocity graph. And that is the end of my lab.